To find the number of theoretical plate n equals to 16, multiply with retention time divided with width of the base to the power of 2. For column 1 of component B, the retention time is 10 minutes, while the width of base is 1.2 minutes. To obtain the theoretical plate 16, multiply with 10 divided with 1.2 to the power of 2. We'll get 1111.11. For column 2 of component B, the retention time is 10 minutes, while the width of base is 2.2 minutes. The theoretical plate is 16 multiplied with 10 divided with 2.2 to the power of 2. This will get 330.58. In conclusion, column that produces peaks with narrow bases will be more efficient and have greater n value, while column that produces wider peaks will be less efficient and have smaller n value. This is because smaller denominator will yield a larger overall number, and larger denominator will yield a smaller number. Moving on, to find the peak resolution, we need to minus the value from both retention time and divide with the value from baseline width for the first eluting peak plus baseline width for the second eluting peak, which will be divided with 2. For the first column, retention time is 8 minutes, while width for the first eluting peak is 1 minute. Retention time and baseline width for the second eluting peak are 10 minutes and 1.2 minutes. When calculated, this is obtained 1.82. For the second column, retention time and baseline width for the first eluting peak are 8 minutes and 2.3 minutes, while retention time and baseline width for the second eluting peak are 10 minutes and 2.2 minutes. Put this inside the formula and this will give us a value of 0.89. To conclude, for column first, resolution is more than 1.5, indicating baseline resolution has been achieved. Peaks are well separated with minimal overlap, while for column second, resolution is less than 1.5, indicating incomplete resolution. This means the two peaks are not adequately separated, meaning they are lightly overlapping and too close together. In conclusion, based on the calculation, column 1 is more efficient for chromatographic separation of component B, as it has a higher number of theoretical plates, which is 1111.11, and achieve baseline resolution with a value of 1.82. Thus, the more theoretical plates there are, the greater resolving power, which means the number of equilibrium states is greater.
Moving on, let's look how to predict the order of the three compounds given below in a reversed phase HPLC. The three compounds given below are benzene, nitrobenzene, as well as anisole. In a reverse phase HPLC, the mobile phase is polar as well as the stationary phase is nonpolar. In order to determine the order of the compounds in a reversed phase HPLC, the polarity of the compounds as well as the mobile phase and stationary phase must be considered. Comparing the three compounds given below, benzene is the nonpolar, hence having the longest retention time. Benzene is nonpolar due to its symmetrical molecular structure, therefore it spends more time with the stationary phase than the mobile phase, meaning it interacts strongly with the stationary phase than the mobile phase. Next is anisole. It has medium retention time, longer than the nitrobenzene but shorter than the benzene. This is due to the presence of methoxyl group, which is an electron donating group. The presence of methoxyl group in the anisole compound slightly increases the polarity of the anisole compound. However, it has a hydrophobic nature due to the benzene ring as well. Therefore, the interaction of the compound with mobile phase is greater than its interaction with the stationary phase. Last but not least, nitrobenzene has the shortest retention time. This is because it is the most polar among the other compounds and it interacts weakly with the nonpolar stationary phase. The polarity of the compound is due to the electron withdrawing nitro group. And that is how we predict the order of different compounds in a reversed phase HPLC.
Question 3. The IR spectrum. First of all, the region below 1400 cm -1 is known as the fingerprint region, which is unique to each compound and often used for identification. In this analysis, we will focus on the region above 1400 cm -1 as it provides information about the functional group present in the compound. The first bulk of interest is the peak observed at approximately 3023 cm -1. This peak is associated with the sp2ch stretching vibration, which is a defining feature of the alkene functional group. In alkene, the carbon-hydrogen bond attached to the sp2 hybridized carbon produce stretching vibration at slightly higher frequencies compared to the sp3ch bond. The presence of this peak is a clear indication of an alkene. Moving to the second region, located just below 3000 cm -1, we see a series of peaks corresponding to the sp3ch stretching vibration. These vibrations are characteristic of alkane chains attached to the double bond. Peaks within this range, specifically between 2850 cm -1 and 2950 cm -1, indicate the presence of single bond between carbon and hydrogen in alkane group. This complementary region highlights the presence of saturated hydrocarbon chains that may be connected to the unsaturated alkene group. Finally, the third region of box is the peak observed at 1660 cm -1, which corresponds to the C double bond C stretching vibration. This peak is another defining characteristic of the alkene functional group. The stretching of the carbon-carbon double bond in alkene occurs at lower frequency compared to triple bonds but remain distinct from other functional groups. The presence of this peak confirms the double bond location within the molecule. Moving to the second spectra, I'm going to explain the key features observed in this IR spectrum and how they correspond to the molecular structure of this compound. First, let's focus on the NH stretch, which is visible as a broad peak in this region between 3300 and 3500 cm power of -1. This peak is characteristic of the stretching vibrations of the NH bond, which is typical for functional groups such as amines or amides. In this case, the NH stretch confirms the presence of an amide group in this molecule. Next, in the region between 2850 and 3000 cm power -1, we observe the CH stretching peaks. These peaks correspond to the CH bonds present in the alkane chain of the compounds. This part of the spectrum reflects the presence of alkyl groups such as CH3 and CH2 groups attached to the molecule. Now, let's move on to the last one, which is the C double bond O stretch, which appears as a sharp and distinct peak in the range between 1650 to 1750 cm power -1. This peak indicates the presence of the carbonyl group C double bond O. Specifically, in this spectrum, the carbonyl group is part of the amide functional group, confirming the structure of the compound as an amide derivative. So this concludes my explanation for this IR spectrum. Thank you for watching.